What do we hear? What is hearing? How do our ears work? And why are hair cells so important, and what happens if we lose them? We hear sounds, vibrations that spread in air or water and stimulate our ears. Hearing is the result of the collaboration between the ear and the auditory brain. An ear without a brain is like an unplugged microphone, but without ears we would not even be able to imagine what a sound was like. Once captured by our external ear, the vibrations cause the movement of the eardrum. Sound is amplified by the middle ear and transferred to the inner ear or cochlea, which transforms the sound vibrations into a neural signal. The auditory nerve feeds this coded message, which contains all of the sound's attributes, to the brain, where different structures work together to create the perception, "I can hear." When awake, the process of hearing involves three different brain levels: a reflex level, where the arrival of the message may cause us to jump or turn our head; the auditory cortex, where the sound is perceived; and other brain areas, which allow the perception to become conscious, recognize the sound by comparing it to those that have previously been memorized, and determine an appropriate voluntary response. When asleep, our ears and auditory pathways are still working and reflexes can still occur. But the other brain regions involved in emotions, motivations, memory, etc. are inactive. There are therefore no voluntary responses or conscious perception. The ear is composed of three parts: the external, middle, and inner ear. The ear canal is closed off by the tympanic membrane, or eardrum. In the middle ear, the eardrum is mechanically linked by the ossicular chain to another membrane, which closes the inner ear. The hearing part of the inner ear is rolled up into a spiral called the cochlea. Sound waves are cut by the external ear and pass down the ear canal until they reach the eardrum and make it vibrate. The ossicular chain then mechanically transmit the vibrations to the liquid of the cochlea. Inside the cochlea are hair cells, which translate sound vibrations into neural signals. By zooming in on a transverse section of the cochlea, we can see the organ of Corti, which contains the sensory hair cells, and one single hair cell and its connection with the auditory nerve. After the sound has been translated by the hair cell, neural signals are sent to the brain through the auditory nerve. Why are hair cells so important? Providing that they have developed normally, our cochlea only contains 15,000 hair cells, and these cells do not regenerate. We can clearly see the hair cells. They are being bent by the sound vibrations, which cause the hair cells to become excited and create a neural signal. Providing that the sound transmission is not altered and the brain works normally, our hearing is fine. In normal hair cells, we can perfectly discriminate the frequencies of sound on the musical scale. What happens when hair cells degenerate? In this image, outer hair cells, the more fragile type, have degenerated. However, inner hair cells are still there. This corresponds to a severe hearing loss and, moreover, a severe loss of pitch discrimination. Language intelligibility is strongly altered. Without the outer hair cells, we can hear some background sound, but barely distinguish the musical scale. Listen. In this image, all hair cells have disappeared. This, of course, results in total deafness. Presbycusis is a progressive hearing loss with age. This type of hearing loss concerns mainly high pitches. When it affects the speech frequencies, it becomes a handicap, usually by the age of 80 or 90. Presbycusis may be accelerated by injury, such as loud noise exposures. Therefore, the handicap may start at a much earlier age, which may result in having, at 40, a 90-year-old cochlea. This sound level scale, in decibels, classifies the sounds in our environment into 4 categories. Up to 80 decibels, there is no risk for the ear, regardless of the duration of the sound exposure. From 80 to 90 decibels, we are getting closer to the danger zone, but the risks are limited to very long exposures. Above 90 decibels is the danger zone. The louder the sound, the less time is needed for damage to occur. Exposure to high sound levels can cause irreversible damage to our hair cells, resulting in deafness and tinnitus. This animation represents the havoc caused by too loud a sound on one of our sensory cells. At about 90 decibels, the hairs may be gradually damaged and eventually the hair cell finally dies. If too many hair cells die, we lose our capacity to hear.